Hello everyone. This is going to be a video to show you what are the benefits of a third order trajectory planner. Quantum, as you can see on the screen here, looks exactly like Mach 3 because it is of course based on Mach 3. The cosmetic changes have not yet been done to it, but some of the functional changes have already been done. The trajectory planner is now a third order planner. And as I said, that's led to a few questions about why the heck would I want a third order planner and what is a third order planner. So I thought it might help to just show you graphically what a third order planner does. First thing I'm going to do is turn off third order planning by setting a very high jerk value here. And now I'll show you what normally what Mach 3 does with a particular move. I'm going to turn on a velocity scope so that we can see the actual moves that we generate. And I'm going to move G0x10 here. And over here on the toolpath of the screen, you can now see that we have a trajectory profile. This is the move that we just did from G0 x0 to G0x10. You can see we got a rapid acceleration up to the traveling speed, which is the rapid G0 speed of the x-axis. We then traveled along this straight line with no further acceleration, simply the velocity of the move, and then we decelerated to 0. This is pretty common in trajectory planners, and it's called the bang-bang method of acceleration. It produces, however, 4 points of jerk on your table. As your axis takes off, way down here at the bottom left of the screen, it's like being in a car and throwing your acceleration on full. Your table, therefore, if the axis is moving to the right, your table will actually jerk to the left at that point. How much it jerks to the left depends on what your acceleration setting is in your motor tuning. The mechanics of many tables force people to turn down their accelerations, otherwise this jerk at this point in time is quite heavy, and your table can actually rattle back and forth. Now there's a second jerk point, which is this point here. This is the point at which your acceleration turns off and you basically begin to coast at a set speed through the move until you reach an x of 10 at this point here. However, when you turn off the acceleration, it causes a mechanical jerk. Your table then jerks to the left. When we get down to this end of the move, we get another jerk as we begin to apply the brakes to slow down to 0. And at this point, when we actually hit 0, it's exactly like being in your car. When you finally do stop, you jerk forward in your seat. These 4 points cause a lot of mechanical damage to your ball screws, the mechanics of your table. It shakes your bolts loose and so on and so forth. It is not an optimal thing to have. Now, Mach 3 blends moves together as an object gets through. Let's load a program here, and we'll just load the Roadrunner, which is our typical test program. Okay, we'll go back to the big tool screen. So here's our Roadrunner. Now, at the bottom of the screen, you're always going to see the profile of velocity. This is not a positional graph along the bottom. This blue line is actually just showing you the velocity of a particular move, and it leads slightly to the actual position of the crosshairs here because the profiles are being generated in advance of the actual motors moving. So be aware that there's a bit of a time lag between the bottom section of this velocity scope and the actual moving toolpath. So let's start the Roadrunner running, and you will begin to see the mixture of moves. Now you'll notice when we're traversing down a straight line, the velocity path is showing that we're at a pretty constant velocity, but now you begin to see the jerk points. Every time your axis changes direction, your table jerks. And these little spikes that look like heartbeats along the way, these are very normal for Mach 3. They've always been there. They're there in most trajectory planners. And these are spikes of jerk, basically. They're a very rapid change in the velocity of your table. When people complain of doing 3D jobs and the machine is jerking all over the place, this is what is causing the jerk. So we're going to stop this. I'll just put a feed hold on it. And I'm going to go up to the path smoothing functionality of the system. And we're going to change this to a jerk of 1500 millimeters per second cubed. This just set a jerk constraint, telling the system that we don't want our table to jerk any more than 1500 millimeters per second squared throughout the toolpath. So we're going to restart the toolpath, and you immediately see the difference. The table is no longer jerking at any point. It is smoothly accelerating down and back up as it generates its way through the waveform. You can see by the crosshair that we're not moving appreciably slower than we were moving before. We have simply connected all the points with a polynomial function which smooths the transitions between any speeds. And the resultant velocity waveform is much cleaner. Now if I stop this and we go to our MDI path, I can show you a single movement. After zeroing, I'm just going to say G0x10 again. And now you can see on the screen, I'm going to flick back to my big tool path, you can see an S-curve profile. Now you can see by looking at the profile we have a nice S-shaped acceleration ramp and a nice S-shaped deceleration ramp. It's that gets rid of the jerk points at the corners. So as I said, as we run the job, you can now see that we get a pretty smooth joining of the sectors. That is the function of a third-order trajectory planner, and it should make a huge difference on some of the tables which aren't quite as mechanically strong as perhaps they should be, or running with a servo or stepper motor that doesn't quite have the power that it should have to drive the table appropriately. Anyway, that's the work so far that's done in Quantum in regards to trajectory planning. I just thought you'd like to have a quick pre-look at how that works. Thanks.